everyone, my name is Mathilde, I am from Kudelski Security, and I am very happy to be here and to welcome you to the presentation, Taking the Quantum Leap with Go. So a bit of background before we start. The library I'm going to present was developed as part of my master thesis, so this is technically a joint contribution between Kudelski Security and my university EPFL. So about me, I enjoy working with all kinds of crypto and eventually apply them towards privacy-enhancing technologies. I would like to mention and thanks one more my supervisor, Yolan Romaye. At Kudelski Security, we are studying state-of-the-art technologies, actively involved in research. We also run a crypto blog and provide quantum-resistant security services. Because what's more state-of-the-art than post-quantum cryptography? So let's start with a quick introduction. Just like classical computers work with bits and logical gates to create softwares, quantum computers use qubits, and this enables them to perform some computation way faster than any classical supercomputer could. This has a lot of benefits in many areas, such as health, finances, pharmaceuticals, but the problem is that it also threatens the security of the cryptographic algorithms that we know and use nowadays. So quantum attacks, basically quantum algorithms run on quantum computers, totally break the security of public key schemes such as RSA, meaning that such algorithms will not protect your sensible information when facing quantum adversaries. Symmetric key and hash functions are also impacted, but not broken. Their security is weakened, but can be fixed by increasing the key size. So you might be wondering, yeah, but why can't we just get rid of public key cryptography then if it's broken? The problem is that we are using public key cryptography all the time in our online world, whether it is to store an encrypted password with GoPass, using some SSH with traffic, encrypting emails, using virtual private networks, or exchanging cryptocurrencies. All of these projects rely on the security of public key cryptography. So it is very much needed. But not all is lost, right? There exists a new kind of cryptography, namely the post-quantum cryptography, which, as its name states, is quantum resistant, meaning that in addition to being resistant to attacks that run on classical computers, it is also resistant to these new kinds of attacks run on quantum computers. There exist many classes of post-quantum cryptography that offer different kinds of trade-off. For example, a lower runtime, a lower bandwidth, and it is important to know your application and your setup in order for you to choose the best kind of post-quantum cryptography to use. So if you're wondering when should you start thinking about using post-quantum cryptography, the correct answer actually was yesterday, because the process from scratch to actually complete transition to post-quantum alternatives is extremely long. It works in few steps that include the research and standardization process, where we're at, the deployment of the implementation, and then the integration of the said implementation into the security infrastructures, right? A problem arises from the fact that we don't know how long do we have before scalable quantum computers are accessible to attackers. And if it is the case before the transition to post-quantum alternatives is finished, then we're potentially exposing our data, whether it is messages, banks information of passwords, to the quantum attackers. We have no idea of how long it will take for this quantum computer to be built and accessible to attackers. But we should not overestimate it, just like the way that Git did it, for example, with SHA-1. So for the story, SHA-1 was known to be vulnerable since 2005. But Git waited and waited, and it took a really long time to finish the transition from SHA-1 to the safe alternative SHA-2056. And actually, an attack was mounted in 2012, if I'm correct. And attackers created a collision on SHA-1, and this had disastrous effects on some repositories. So if Git were to have been faster in this transition, this attack would not have been possible. And the process in quantum computing has been really fast. So as I mentioned, quantum computers now are prototypes, right? Attackers cannot really break the keys and security level of the things that we use nowadays. But it is a matter of years before fully functional computers are accessible. And we should not wait more because, as we saw with a few examples, crypto agility, so changing crypto primitives, is a true challenge. And moreover, we cannot simply run with the fact of, but can't we increase the key sizes? Because if you want something that is somewhat quantum resistant, then, for example, for RSA, you would need to use 1 terabyte large keys. Not very practical. And before I introduce our library, I would like to give a little crypto refresher. So I talked about public key cryptography. And public key cryptography has two main uses. The first one being authentication. And authentication is given by digital signature algorithm, shortened to DSA. Digital signature algorithms produce a signature on a message given a secret signing key. The signature can then be checked, verified against the message, and a verification key that is openly disclosed. The DSA have the unforgeability property, meaning that it is very hard to produce a valid signature without actually knowing and holding the secret signing key. And in that case, DSA actually do provide authentication because a signature, in that case, is the proof that the signer knows and holds the secret signing key. A second case where public key cryptography is very useful is for encryption. The thing with public key cryptography and encryption is that it is extremely slow, and people want a fast internet. So this is why public key encryption is mainly used in hybrid encryption schemes. Hybrid encryption schemes are a specific case of encryption where the public key part is used to transmit securely a symmetric key. And the said symmetric key will later on be used to exchange the actual data via symmetric encryption, which is way faster. And so this step of encapsulating the symmetric key and securely transmit it is obtained with key encapsulation protocols, shortened to KEM. So in our CrystalGo library, we propose both a DSA, dilithium, and a KEM, Kyber. Both Kyber and dilithium are quantum resistant and very good candidates for the post-quantum area. They both are finalists in the NIST standardization competition. And if you want more technical details, they are lattice-based, and they stood out to us because of their simplicity, tight security, and overall versatility. Both have a very high performance, and as you will see, they can even excel some of the classical schemes that we use nowadays. The main drawback of the Crystal suite is their relatively large output size. And when I say output, I mean public key, ciphertext, or signature size. It will impact the performance of your project, but it will never be a bottleneck just like a 1 terabyte key could be. So really our contribution is that we ported the reference implementation of the Crystal algorithms from the original C language to Go. We make our implementation open source and available at the following link, but we also included the QR code for faster access. At Kudelski Security, our mission is really to focus on practical security. So the theoretical part was dealt with the Crystal papers, which include tight security proofs, which were reviewed and confirmed. So we put a lot of effort into having an implementation that is secure, and we integrated as many security features as possible. We want this security process to be continuous. So we encourage you to open issues on our GitHub, either to challenge our code or just engage in some kind of discussion. I will now present our API and demonstrate how easy to use our library is. So the flow of Kyber and dilithium is very similar. It works in 2 steps. First, the user has to choose a security level they want to work with. And this will define all the parameters that are used internally so that no mistake is made. And once all the parameters are defined, then the core functions can be used. Our library also has helper functions other than the core functions, but I will not go much into the detail as I want to say very high level. If you want to learn more about all the features that our library has, I suggest to go and read the README. So the two steps that I mentioned are really clear when looking at the API. So the functions are really divided into two groups. The first group are the type functions that define a dilithium instance with a specified security level. So from top to bottom, we have an increasing security level, meaning that dilithium 2 is the lightest scheme, while dilithium 5 is the strongest scheme in terms of security. Then, once the parameters are defined, the core function of dilithium signature can be invoked. And the core methods are, of course, the key generation functions, the signature, and the verification functions. Code-wise, it looks like this. First, the user wants to go and have a signature protocol, agree on a security level, and create the dilithium instance. Then, on this dilithium instance, they can call the core function. So the first user, for example, generates the verification and signing key pairs. The public verification key can be openly disclosed. Then when the first user wants to sign a message, he can take his signing key, the message, and produce a signature that can be transmitted along with the message, and checked again the public verification key that the second user receives early. If everything went fine and the users are honest, then the Boolean returned by verify is going to be true. Similarly for Kyber, we have two groups of function. So from top to bottom, we also have increasing security, meaning that Kyber 512 is the lightest and Kyber 1024 is the strongest in terms of security. So Kyber being a key encapsulation mechanism, the core functions are different. Now we have the key generation function that creates a public and secret key pair, and we have the encapsulation and decapsulation functions. The encapsulation function, given a public key and some coins, creates a shared secret and the encryption of the said secret. So the encryption of the shared secret can be transmitted to the secret key holder for it to be decapsulated and thus the shared secret recovered. So for a practical example, similarly, the user have to agree on the security level they want to use. In that case, they want to use light security. They create the Kyber instance and invoke the core functions. So following the flow of a KEM, the first user generates the public and secret key pairs, openly disclose the public key, and the second user can now engage in the encapsulation mechanism by taking this public key and generating a shared secret and its encryption by calling encaps. The ciphertext can be shared back to the first participant, who can use his secret key to recover the shared secrets. In our case, the value of SS is going to be the same for both participants and can be used as symmetric key material to then go further into this hybrid encryption process. Performance-wise, what do we have? So if we're talking about security, our library is both theoretically and practically secure. In comparison to the other libraries that provide the Crystal suites, we integrated countermeasure for many of the published implementation attacks, so namely the side channel attacks. Regarding the runtime and the size of the outputs, we reported in this table the numbers for the recommended security level, so which is the medium one. And you can see that a function call takes from a fraction up to 2 milliseconds, and the size of the outputs ranges from 1 megabyte to 3 megabytes. So we thought that this number might give you some idea of the practicality, but still be a bit abstract. So what we did is that we actually compared the performance of our library against the library that are contained into the Go crypto official package. So we compared dilithium against ECDSA, and Kyber against RSA OAEP for an equal security level, of course, in the classical setting, because ECDSA and RSA are, of course, broken when facing quantum algorithms. And as you can see, our library in blue is actually way more performance in terms of runtime than the Go crypto implementations highlighted in orange. But the trade-off becomes evident when looking at the bandwidth that is being used. Just as I mentioned, the output size of the Crystal suite is way larger than what we used to deal with. Nevertheless, we wanted to test the practicality of our library. So what we did is that we implemented it and integrated it into the WireGuard protocol. And when adding quantum resistance to the WireGuard protocol, well, spoilers alert, it is still practical. It has an overhead of 0.2 milliseconds regarding the runtime and requires sending 2 extra IP packets. This overhead is totally acceptable, especially knowing that the transition towards post-quantum schemes must happen with the arrival of quantum computers. And if you want more details, we encourage you to attend our talk at the NIST for the standardization conference. So to conclude with, we presented a library that is fast, secure, and easy to use. And we furthermore showed you some experimental results that you should use as motivation to start integrating post-quantum cryptography in your project. As last word, I would say that if you're going to use cryptography, any kind, you should make sure that it is very safe, especially regarding implementation security, which is often overlooked, and make sure to use libraries that are secure in that aspect, just like we made sure to do with ours. So I hope that you enjoyed this presentation. If you want to learn more about post-quantum cryptography in general, I added some other material that might be of interest to you. So thank you very much for your attention, and if you have any question, feel free to contact me.